Okay, hello everyone. Let's take a look at anti-differentiation. Now let's put anti-differentiation into perspective and see where it fits. We said that there are two types of integration. One, there's the definite integration, and notice that this is the way that we went ahead and wrote that definite integration, is by using the integral sign from a to b of f of x d of x. And what we've shown is that this is actually going to be a number, and it's going to represent the area that is bounded by the curve f of x, the positive x-axis, or just the x-axis, as well as these vertical lines x is equal to a and x is equal to b. Now the other type of integration is going to be called indefinite integration. And what indefinite integration is actually going to look like is this. Now notice the only difference between this part here and this part there is that we don't have the a and b. But it's because of that essential fact that we're going to call this indefinite integration, and what we're going to come out with is something that is completely different. It is actually going to be, the result is actually going to be a function plus what is called c. Okay? So what we have here as a result of definite integration is a number. The result of indefinite integration is actually going to be giving you a family of functions. Okay? Now, let's go ahead and just make sure that we're clear with some of this notation. If we were to go ahead and take a look at the f prime, capital F prime of x, that is the same thing as f of x. Okay? Now, what does that mean? What that means is that the process of integration and this process here of the process of differentiation and indefinite integration are actually inverse operations of each other. Okay? So that's why we say that if we take a look at this capital F prime of x, it is actually going to be the same thing as f of x. Okay? And c, this c here, is going to be called a constant of integration. Now when we get to class, we'll go ahead and decide to look a little bit more as to what that c actually represents and how it affects this particular function here, so that we have a family of functions. But let's go ahead and take a look more at what anti-differentiation is. And basically what we want to do is we want to juxtapose them between differentiation, because we said before that differentiation and anti-differentiation are really inverse operations of each other. So let's just go ahead and take a look at this. If I was to start off with a capital F of x, and if I was to differentiate that, what would I come up with? So if I take a look at capital F of x is equal to k, if I differentiate both of them, basically what I come out with is 0. So notice that if I take the derivative of both sides here, the derivative of capital F of x is capital F prime of x, which is going to be the same thing as f of x. So we're going to call that f of x, and that of course is going to be equal to 0. Now, if I go ahead and take a look at this here, hopefully everybody recognizes this. This right here will be your power rule. Notice again, I'm taking the derivative of both sides, left and right hand side, so that this becomes f of x, because that's the derivative of capital F prime of x. This here, notice I'm using the difference between the capital Y and the lowercase y. So the derivative of the capital uppercase Y is the lowercase y. And hopefully all of you recognize what rule this is. This is just going to be the scalar multiple rule. This here again, notice I have a capital Y, a capital F, and a capital G. If I take the derivative of both sides, hopefully you recognize that this is just the sum and difference rule. Okay, and if we go ahead and take a look at the capital F of x is equal to e to the x, take the derivative of both sides, we come up with just f of x equals e to the x. And if we go ahead and take a look at the logarithm, then of course f of x is going to be equal to 1 over x. So all of you are familiar with how to go from differentiation, how to differentiate a function. And all we need to do at this point right now is just make sure that we know the difference between the capital F of x and the lowercase f of x. The reason why that's so important is because when we actually anti-differentiate, we're going to undo what differentiation did, so that if we start off with this, we're going to come back to this. So notice that's the inverse property of differentiation and anti-differentiation. So if we go ahead and start off here, let's go ahead and say that if you started off with a function f of x is equal to k, if you anti-differentiated that, then basically what you would come up with is this capital F of x, because that is the original function, let's just say. And if I was to go ahead and find out what that would be, that would just be kx plus c. Now, let's go ahead and just make sure we understand exactly what this means. If I was to take a look at the derivative of this, I had better come up with this. Okay, so if I take the derivative of capital F of x, notice that that would give me little f of x. If I take the derivative of this side, I would just come up with k, because of course c is a constant, so when you take the derivative of a constant, it becomes 0. So the antiderivative of this is always going to be equal to this. Okay, same thing with the power rule. The power rule is a little bit different, just because of the way that it looks. Let's say, for example, that we started off with f of x is equal to x to the n. Okay, if I wanted to do the antiderivative version of the power rule, again, f of x would come out to be a capital F of x. But what I would have to do then is I would actually take 1 over n plus 1, x to the n plus 1, n plus c. Now, let's again check. If I was to differentiate this here, do I come up with that? So the capital F of x, take the derivative of that, I come up with this. If you take the derivative of that using the power rule, I take the n plus 1, I multiply it to this, that becomes 1, and I subtract 1 from that, and I just get x to the n. The c will cancel because that's going to be a 0 when you differentiate a constant. So that is going to be your power rule version of antidifferentiation. Same thing here with the scalar multiple rule. Notice that if I take the derivative of both sides here, then I come up with that. So if I started off with this and I wanted to antidifferentiate, this is what I would come up with. If I was to do this for this sum and difference rule, notice that everything stays the same except for I just add the c, which is the constant of integration. Same thing with the original function e to the x. Notice that the capital F of x is equal to e to the x plus c. And notice that with the logarithm here, if I started off with f of x is equal to 1 over x, then the antiderivative would be capital F of x and the natural log of the absolute value of c. That's going to be an important point. The absolute value of x, and then plus the constant c. Okay, so what we're going to have to do then is when we get to class and we have some time together, we're going to have to make sure that if you're given this, if you're given a particular function, regardless of what that function looks like, you can actually find out what the antiderivative would look like, or what that antiderivative function would be. Okay, and we'll practice that when we get to class. So, just to summarize, two different types: definite integration, indefinite integration. They give you two different things. Definite integration gives you the area. Indefinite integration gives you a family of functions with the c as the constant of integration. And there's the relationship there to show you that differentiation and anti-differentiation are inverse properties of each other. Okay, so let's see how you do with anti-differentiation. We'll take a look at some examples in class. Okay, see you later. Bye.